Ok, well. Ah, est-ce qu'il faut que je fasse quelque chose? Non. Sorry. Okay, well, thank you very much for inviting me. It's a pleasure to speak at this seminar. And indeed, I'm going to talk about quantization methods in the Yau-Tian-Donaldson program. So first, I'm going to give an overview, a short and brief overview of this program, and especially focusing on the aspects that interest me in this talk. Then I'm going to start introducing what I call the quantization methods in this program through the notion of balance metrics. Then I'm going to talk more specifically about the tools of berezin-Toeplitz quantization that I use to approach the balance metrics. And finally, I will end, if time permits, with a brief review of proofs of the main results, which is related to quantum noise of berezin-Toeplitz quantization. And I forgot to say this talk is partly joint works. It's based on joint works with Leonid Polterovich and also Shmoish and withVictoria Kaminker. Okay, so first the Yau-Tian-Donaldson program. So the basic object of my talk will be a projective manifold. That is a complex holomorphic submanifold of the projective space of dimension n for some n, right? And I will write small n for the dimension of x. And since it's a complex manifold, it has a complex structure, which induces what's called an almost complex structure on its endomorphism of the tangent bundle, which I write J. So J square equals minus identity. Okay. Then the basic property of a projective manifold is the fact that the Hermitian metric, it has an Hermitian metric on its tangent bundle, induced by the fubini study metric of CPN, the canonical metric of CPN, and this metric is Kähler, meaning that the two form, which is defined that way with G and the complex structure J, is closed, because it is the case for the two form induced by the fubini study metric. Hence, it stays closed by restriction. And the fact is that the existence of a Kähler metric on a complex manifold has strong consequences on the complex geometry of this manifold. And the most celebrated consequence is the so-called Hodge decomposition of its de Rham cohomology into Dolbeault cohomology groups, right? So Kähler metric is a useful tool in the study of the complex geometry of a projective manifold in particular, right? But one key remark for this talk is that such a Kähler metric induced by a projective metric is not canonical, and even the fubini study metric is not canonical. Indeed, GLN plus 1 acts on the projective space of lines in Cn plus 1, preserving the cohomology class of this closed form, but not the form itself, and hence not the Kähler metric. So actually, you don't have one fubini study metric, but a whole family parameterized by GLN plus 1 up to UN, right? So it's the same, and the same is true in particular for the restriction to X, right? So the basic question of this talk and of the Yau-Tian-Donaldson program is the existence of a canonical Kähler metric in the space of Kähler metrics in a given cohomology class, here, which I take here to be this specific cohomology class, so projective class, right? So, and we want to know, among all these Kähler metrics, is there a better one which has remarkable properties, and such that with these properties, it will have even stronger consequences on the complex geometry of X. So it will be even a better tool for the complex geometry of X, right? So the fundamental example, which is a guide for the whole program, if the case when the complex dimension of X is 1, that is the case of Riemann surfaces. In that case, you have the famous uniformization theorem, which tells us that there exists a unique Kähler metric with constant scalar curvature, up to scale, of course, and up to the automorphism group of the surface. Here, scale means a multiplication by a positive constant, right? It stays of constant scalar curvature in that case. And indeed, this theorem has strong consequences on the complex geometry. In particular, if the constant scalar curvature is strictly positive, it implies that X is actually CP1. If the scalar curvature is 0, the metric is flat. So it implies that X is a quotient of C by a lattice, a torus. And for when the scalar curvature is negative, this implies that X is a quotient of the hyperbolic space by, again, a discrete subgroup, right? And this, of course, has, so if the first two statements are actually much more basic, the real content of uniformization theorem is this last statement. And indeed, the fact that we know that surfaces of genus 2 or more, which is the case here, are quotient of the hyperbolic space is a very strong consequence on the geometry of X and has a lot of application in the study of such surfaces, right? And all this given by the existence of a constant scalar curvature metric, okay? Which is our notion of canonical metric here. And just a remark, here the cohomology class does not appear because H2 of Z is simply Z, right? And the cohomology class reduces to the scale. So actually here, the role of the cohomology class is simply no, the other way around. In general, the cohomology class will play the role of the scale in the case of Riemann surfaces. So it's a very natural condition to fix a cohomology class. Okay. So now to describe this case, the general case, I will still focus on the specific case when the projective class is proportional to the first-Chern class of X. Sorry. So I forgot to remove, before there was lambda here for some lambda in R, but actually it's enough for my purpose up to scaling to consider either plus or minus the first-Chern class of X. All right. So why is this useful to do so? Because in that case, a metric is of constant scalar curvature if and only if it is Kähler-Einstein, meaning that the metric is proportional to the Ricci tensor up to a constant, up to lambda, which here is plus minus. Okay. And this has, again, wonderful properties, and it's easier to study than constant scalar curvature. And in particular, there is a famous theorem of Aubin and Yau telling you that if this lambda is minus, so in the case of the minus first-Chern class of X, then there exists a unique Kähler-Einstein metric up to the automorphism group. And they use methods of geometric PDEs, which are nonlinear PDEs of order 2, which then manage to solve, right? It's to be compared with geometric PDEs involved in the constant scalar curvature equation, which are of order 4, much harder to deal with, right? Okay, but in the case of plus C1S, the first-Chern class of X, there are obstructions to the existence of Kähler-Einstein metric. So this theorem is not even true. And in particular, there is this theorem. So actually, it's two theorems, one of Matsushima and one of Futaki. I just put it in one box, let's say, that it tells us that if there exists a Kähler-Einstein metric with in the first-Chern class of X, then the automorphism group, so the group of B-holomorphic diffeomorphism of X, is a reductive group. So it's always a finite dimensional Lie group. But then if there is a Kähler-Einstein metric, it's reductive. So it's one strong consequence of the existence of a Kähler-Einstein metric in this case, by the way. And the so-called Futaki invariant, which is a map from, which is an holomorphic invariant from the Lie algebra of the automorphism, so holomorphic vector fields to C, vanishes identically. So I will not give the definition of the Futaki invariant. It's enough to say that this can be computed in many cases. And if you find not zero, then you know there is no Kähler-Einstein matrix, right? And there is a result of Burns de Bartholomeis following this, which showed that these two conditions are not sufficient in general. It's not true that if Futaki invariant vanishes and automorphism group is reductive, then there exists a unique Kähler-Einstein. It's not sufficient, and they constructed example of ruled surfaces, so projectivization of vector bundles, and they showed that existence of Kähler-Einstein is related to the stability of these vector bundles in some specific case. Stable will imply existence, non-stable implies non-existence. So this motivated Yau to state this general conjecture, which tells us that the existence and uniqueness of a constant scalar curvature metric, so back to the most general case, in some projective class, is equivalent to some complex algebraic stability condition on the complex manifold X, the projective manifold X, right? Relating Riemannian geometry of X with complex geometry of X. So he did not say what is this stability condition. So there are lists of properties that a stability condition should have, but this is part of the conjecture. And Tian, then Donaldson, in their study of this program, introduced the appropriate condition called K-stability, which I will not introduce because I will not use it in this talk, but it's enough to say that they found the correct condition. And finally, the conjecture in the case of this case of C1X has been shown true by recently by Yau-Tian-Donaldson and Tian, which kind of was a pinnacle of Yau-Tian-Donaldson program in the case of Kähler-Einstein matrix, the constant scalar curvature case being still open. All right. So this was a brief introduction to the Yau-Tian-Donaldson program. But today I will focus on one specific aspect, so not on K-stability, but something that appeared before, and which is a study of balanced metrics in this program. So to introduce balanced metrics, I will need to get a little bit more into details and recall you that for a holomorphic line bundle on X, so these are simply notations that if we have a holomorphic line bundle of X, I will write LP for P, an integer for the PF tensor power of E, L, so L tensored with itself P times. And I will set HP for the space, finite dimensional space of holomorphic sections of LP, right? And note that the dual tautological line bundle, so there is a canonical line bundle of tautological line bundle of CPN, which to a line in Cn+1 associates the line that it represents. This is a tautological line bundle, but its dual, which is called O1, restricts to a holomorphic line bundle of L of X, some projective manifold, which is ample, and such that the projective class is actually given by the first chart class of L. So I will be able to get rid of this awkward notation from now on and write C1L, okay? And if you were wondering, an ample line bundle is called ample if for all integer big enough and for any basis of the space of holomorphic sections, this map defined thanks to this basis is first of all well-defined and second an embedding, right? So just to describe this map, this S0x is one of x, etc. for some given x are elements and np+1 elements of a complex line. So fixing a trivialization of this line will give you np+1 numbers, complex numbers, and if you change trivialization, these np+1 numbers will all change by the same multiplicative factor. So it gives you indeed a well-defined element of projective space, which means an element up to multiplication by lambda in C star, right? So the fact that this map is well-defined means exactly that for all x, all these numbers do not vanish at the same time. There is no base point. And that this is an embedding is a bit more involved, but here you go. You have this definition, right? And it turns out that the restriction of the tautological line bundle is ample in that sense, right? So from one embedding of X into CPN, we now have a family of embedding in all for parameterized by an integer for all P in CPNP. So now we even vary this embedding. So we have more and more fubini study metrics in particular. And the point here indeed is that given such an embedding, the pullback, so restrictions of O1 on CPNP is L to the P, right? So that in particular, the pullback of the fubini study metric, like in the beginning, but for these bigger spaces, belongs, so 1 over p of this belongs to h of 1 over p of c1 of lp, but by multiplicative properties of the Chern character is simply c1 of l. So for each embeddings, you have families of Fubini study metrics, which are all in this fixed space of Kähler metrics in this Kähler class, right? And this is what is going to interest us. So note first that if you have a base of HP, then it gives you a Hermitian product on HP for which S is orthonormal. And then the famous theorem of Tian, tells you that the image of the Fubini study map, which to the Hermitian product on HP associates the induced Fubini study metric pullback on X, right? This map becomes dense as P tends to infinity, right? So I told you at the beginning that you had gn plus 1 worth of Fubini restriction of Fubini study metric on X. But now with these embeddings, you have more and more Fubini study metrics. And the Fubini study metrics fill the whole space of Kähler metrics when P tends to infinity, right? And the key point here is that the space of Kähler metrics is an infinite dimensional space, while so even it makes sense as an infinite symmetric space. You need to make sense of that, of course. While the Hermitian products on HP is a finite dimensional symmetric space, right? So you can hope to reduce hard geometric PDE equations in an infinite dimensional space to basically linear algebra on a finite dimensional space. So replace analysis by linear algebra for all P. And of course, these spaces are growing when P tends to infinity, right? So the question now is there a finite dimensional notion of a canonical Kähler metric? We would like, so we have the supposed constant scalar curvature metric here. Can we find some kind of canonical metric here to compare it and approach this metric? So every Kähler metric can be approached by Fubini study metrics. So the question is there a notion of canonical metrics here, such that the canonical metric here is approached by these canonical metrics? So it will reduce this hard problem of finding it to an easier problem. And this is exactly what is a balanced matrix. And to describe this finite dimensional notion, we need a bit more tools. So recall, Chern-Weil theory tells you that the space of Kähler metrics in a given class of the line bundle are actually given by so isomorphic to positive Hermitian matrix H on L up to multiplication by a constant. So it should be C star here. Well, it depends how you look at it. But anyway, what I want to say here is that what the so-called positive Hermitian metric on L induces a Kähler metric via its Chern curvature. So if its Chern curvature is a non-degenerate form, then you can define a Kähler metric. And this is the definition of positive. I will not use this definition. It suffices to say that studying Kähler metrics is the same as studying positive Hermitian metrics on my line bundle. Okay. Also, for later record, a Hermitian metric H on L induces a Hermitian metric HP on LP. And the other way around, if you have a Hermitian metric on LP, you can take its P of square root. So the difference here, it's only multiplies this Kähler metric by P. That's why we divided by P before. But okay, you can go from one to the other, right? And finally, given a measure nu on X and a positive matrix on L, we consider the Hermitian products on the holomorphic sections given by the so-called L2 Hermitian products, where you simply use HP to integrate two holomorphic sections against one another. And now I can define the notion of a balance metric in HC1 of LP. It's called new balance if GHP is equal to the pullback of the Fubini study metric for an orthonormal basis with respect to this L2 product, right? So what happens here? You start with a Kähler metric, consider the embedding given by what's called the Kodaira embedding, given at level P. Consider the L2 product on the fubini study metric on CPN induced by the L2 product, pull it back, right? So Kähler metric gives you Hermitian product, then you can pull back the induced fubini study metric. Question: does these metrics coincide? Is this operation evolution? The answer is no, not always, and we call a metric new balance if it is the case. There is also the notion of balanced, which is new balance for the most obvious metrics you could consider, which is the volume form induced by GH, the so-called Liouville volume form, which is also the symplectic volume form of X. Okay? And now the point here, of course, is that balance metrics belong to the finite dimensional image of the Fubini study map, right? Balance metrics are Fubini study metrics, and there is only a finite dimensional, they're parameterized by a finite dimensional space. So it really is a finite dimensional notion. You can, by the way, pull back this notion and call a balanced Hermitian, a Hermitian product balanced if its Fubini study is balanced, basically, right? So we have our notion of a finite dimensional canonical metric, and this is a fundamental theorem of Donaldson, which tells you that if the automorphism group of X and L is discrete, and if there exists a constant scalar curvature metric, then there exists a unique up to automorphism balance metric GP for all P, because the balance condition depends on P, and these metrics appropriately rescale, right, to be in C1L, converge to the constant scalar curvature matrix when P tends to infinity, right? So if you have an infinite dimensional canonical matrix, there exists a sequence of finite dimensional canonical matrix for the good notion, and it tends as to the metric as expected, right? As wished. And as a corollary, Donaldson was able to prove easily that this constant scalar curvature metric, if it exists, it is unique in HC1L up to the automorphism group, right? Because it is the limit of unique balance metrics. So the limit has to be unique. If you had two, then it would be a contradiction. These guys cannot tend to two different metrics. Right, so it proved the uniqueness of the constant scalar curvature metric, and it was the first proof of uniqueness of constant scalar curvature metric. So it has been reproved later on using geometric PDE methods, but the first proof used these finite dimensional methods, if you wish. And the point here is that the uniqueness of balance metrics follows from standard moment map techniques over this finite dimensional symmetric space. So it's actually, if you wish, linear algebra or non-linear algebra, if you wish, techniques. So not hard PDE techniques. So it's you replace a hard PDE techniques by easy techniques, but for each P. So each P. So an infinite sequence of easy techniques, if you wish. And this theorem was a key step in the resolution of Yau's conjecture. Not necessarily because it's end result, but because it provided an insight, and resolution of Yau's conjecture by Yau-Tian-Donaldson and Tian is a full combination of geometric PDE techniques on one hand and these so-called quantization techniques on the other hand. I will come back, of course, later on the term quantization here. Okay, so now assume that this line bundle is actually the determinant of the holomorphic tangent bundle. So that in particular, C1L is equal to C1X, right? So back to the Kähler-Einstein case, if you wish. So these things actually are equivalent, but it's not clear. So let me just state it as it is. So what happens in the Kähler-Einstein case? This is the question now. So this was constant scalar curvature, but I spent some time to tell you about the Kähler-Einstein case. So it is. So there is another definition of balance, also introduced by Donaldson later on, so-called anticanonically balanced, because this is called the anticanonical line bundle, if it is new balance for this metric, right? So in holomorphic coordinates, simply take the flat matrix of these holomorphic coordinates and then use the positive Hermitian metric on the determinant to evaluate the dz1, dzn is simply the vector field in these coordinates and generated by these coordinates. And then it's easy to see, it's obvious by definition, that when you change coordinates, the factors that goes here will be cancelled by the factors that goes here, right? So it's actually globally well defined. Here is the correct factor to make it simply the correct factor to make it a volume form. Right, so it's indeed a volume form, and you can define new balance for this volume form, anticanonically balanced. And then an extension of the theorem of Donaldson in this case, first due to Berman, Buxom, Gage, Zeriahi, but also Takahashi and then myself giving another proof. So it's 3 different proofs telling you that Kähler-Einstein matrix, if there exists a Kähler-Einstein metric and the automorphism group are discrete, we have a sequence of anticanonically balanced metric, unique up to automorphism, tending to the Kähler-Einstein metric, right? The advantage of such an approach is, since the Kähler-Einstein equation is easier, it is also not since, but it is also the case that the anticanonically balanced metrics are easier to study. So there is a parallel. So there is something to be gained to restrict to Kähler-Einstein and study anticanonically balanced metrics. So you will be able to prove more. Although that's not what I'm going to talk about today, right? And again, so these are very different proofs. So Berman, Buxom, Zeriahi used completely different method than Donaldson, using energy functionals. Also, yeah, well, infinite dimensional energy functionals, if you wish. Takahashi managed much later to adapt the strategy of Donaldson, and my proof uses an input based on berezin-Toeplitz quantization, which I will describe. But now, question, what about a general automorphism group, which is not covered by this case and not even covered by the case of Donaldson? And also, what about if the Futaki invariant does not vanish? There is no Kähler-Einstein matrix, but maybe there is another type of canonical metric, another notion of canonical metric. And indeed there is. And a metric in C1X is called a Kähler-Ricci soliton if it's Kähler-Einstein up to automorphism in that sense, right? So here Xi is this is a Lie derivative by Xi, so Xi is a holomorphic vector field, Lie algebra of automorphism of X. So it's Kähler-Einstein up to correction by automorphism. And it turns out that this is a correct generalization in the case the Futaki invariant does not vanish. On the other hand, you can define also equivariant notion of anticanonically balanced metric by the automorphism group in a similar way, that a metric is relatively anticanonically balanced, or relatively balanced for simplicity, if when you consider Kähler metric, takes the L2 product, then put on the holomorphic section, then pull back the fubini study metric, it's not equal on the nose to the metric you started with, but up to an element of the automorphism groups, right? And then later on, I was able to show that if there exists a Kähler-Ricci soliton, then there exists a unique relatively balanced metric for all p big enough up to automorphism, and they converge to the Kähler-Ricci soliton, which gives you as a corollary another proof, finite dimensional proof or quantization proof of a result of Tianzhu, stating the unicity of Kähler-Ricci soliton up to the automorphism group. Right, so they did use the hard PD techniques, so the normal way to show such things, and this gives you a quantization proof based on finite dimensional method, completely different proof. And I also need to point out that this result was already studied by Berman, Wittney-Strom, and Takahashi, who established the convergence in the sense of currents, which is actually not good enough for some other aspects of Donaldson program, which I will not go into. But my own motivation was that I needed the smooth convergence to be able to go further. So this is one improvement, and also under some stability assumptions, which in particular does not allow them to get a new proof of Tianzhu. So their stability assumptions uses the unicity of Kähler-Ricci solitons, right? So Yes, so that's it for our results. Now I will tell you more results, but more about the quantization aspect of this program. And indeed, the spaces of holomorphic sections with L2 product form what is called a holomorphic quantization of X seen as a symplectic manifold, right? Where omega H is the symplectic form associated to the Kähler metric GH. And H is some given positive Hermitian metric here, right? So what does it mean, quantization? But so basically, a symplectic manifold is supposed to it gives you a model for classical mechanics, and its quantization is a model of quantum mechanics associated, such that in some when the scale gets big, so quantum mechanics is at the level of the atom. So when the scale gets bigger and bigger, you want to recover the laws of classical mechanics from the laws of quantum mechanics, right? And here, what plays the role of the scale is this integer p, which represents a quantum number. So the most basic example being in the case when x is s2, then p represents what's called the spin, but it can also represent energy levels or number of particles. And so when energy of number of or number of particles become commensurable to the to us classical world, then you want to recover the geometry of the symplectic manifold, and this is the so-called semi-classical limit. So I will show you examples of such principle shortly. So first I need some tools, basic objects of quantization. And the first object I want to consider is the so-called density of states, which is defined as the following. So so I guess the interpretation is pretty clear. So you want to, is a function which tells you how much you have states, quantum states are concentrated on a given point. So it's the sum of their norm squared for S an orthonormal basis with respect to the L2 product. It's called the density of states, but also in the literature, it is a Berman kernel or Berman kernel restricted to the diagonal. But here we see it as a density of state, and in particular, it's easy to see, I mean, straightforward from the definition, that the dimension of HP is simply the integration of this density of states on the nu. So it's really a local version, I mean, a local replacement for the dimension of the holomorphic sections, if you wish. That's how you should think of density of states. And basic results about this density of states, which follows from work of Boutet de Monvel-Jostron, which has been noticed by Zeldich and Katlin. But here I will tell you a generalized version due to Dai Liu and Ma, is that this density of states admits an asymptotic expansion in powers of p when p tends to infinity. And furthermore, you have that, okay, so first coefficient is a function which simply gives you the difference between d nu and the Liouville volume, symplectic Liouville volume of the manifold. And in particular, in the case when B0 equals 1, so d nu is the Liouville volume form, then we have also a formula for the next coefficient, which is given by the scalar curvature of the associated Kähler metric, right? And what I want to point out here is through the fact that this dimension of HP is simply the integral of rho p, you see, thanks to this formula, that this implies that the dimension of HP tends approaches, when p tends to infinity, the volume of the symplectic volume of X. Basically, the physics interpretation is that the number of particles tend to the volume of phase space when p tends to infinity. So you should think as the phase space X as small cube of size 1 over p, and each cube will fit one such particle. And you can indeed prove that there are highly peaked particles in such cubes, right? That's how you should think. And the scalar curvature in the second coefficient is related to the fact that metric balls, the size of metric balls, are indeed controlled by the scalar curvature. So it makes sense that it's a packing, I mean, it fits into a packing problem for such high peaked states, right? So this is just um, ideas, interpretations, if you wish. It can be made precise, but I will not go into it. Here, I just want to point out the role of this function into Donaldson's program is that it is easy to check. Is actually basically by definition, just write the definition of Fubini study metric, that the pullback of the Hermitian Fubini study metric. So Fubini study metric, this is the positive Hermitian metric on the dual tautological line bundle of CPN, which induces the Fubini study metric, which you can pull back on LP, and the difference with the the metric you started with, when you pull back with an orthonormal basis with respect to L2, is this function rho p. And this is easy, it's a lemma, right? But the crucial importance here is that in particular, a metric is new balance if and only if this metric is constant. It disappears when you get to the Kähler matrix itself, because there is a log, dd bar of a log. So we have a quantum characterization of the balance condition, if you wish, through density of states. And here you can already see the basic link with the theorem of Donaldson. Indeed, assume that there exists. So on the other hand, on the contrary, assume that there exists balance metrics and that they do converge to a limit. It's not the theorem of Donaldson. Donaldson tells that if there is a constant scalar curvature metric, then you have balance metric which converge, right? Assume on the other hand that you have balance metrics and they do converge to a limit. Then this limit has to be of constant scalar curvature. And it's a basic, there are some technicalities, but it's kind of basic consequence of the result due to Boutet de Monvel-Jostron of the expansion of the density of states. And indeed, if you take these functions and they are all constants when p tends to infinity, they are all constant, but when p tends to infinity, they have this expansion. So in part, because it converges, you know also that the scalar curvature converge. But then the fact that this is constant implies that the limit has to be constant, right? So this is really, so the limit has to be of constant scalar curvature. And the theorem of Donaldson is a converse of this basic fact. It's not basic because of the hard asymptotic expansion of rho p, but since you have this, it's an immediate consequence. And the whole point is to get a converse, so to speak, right? And to do so, a basic tool, at least for us, is what is called the Berezin transform, which is defined, at least in the context of, in this context, there is a purely quantum definition, if you wish, but I will give you the definition which fits best in the context as the differential of Fubini study metrics when you vary the positive Hermitian metric. So when you have a positive Hermitian metric H, you can multiply it by a function, exponential of a function, times a very small t. So it stays positive, it's the deformation of the metric. And you can wonder what happens with the induced Fubini study metric, that you take the L2 product and pull back, and what happens with it. Then this is what happens. It's called the Berezin transform, right? And basically, what you should think of is that it is a differential of the map, you know, taking the L2 product and given the Fubini study metric at a fixed point. So in particular, if you consider a fixed point, it will send you, well, okay, sorry. It's true in general, but here, when you consider a fixed point of this map, you can consider the differential. This will tell you that it is a differential at this fixed point. Basically, the tangent space of Hermitian metrics are functions, thanks to this formula. And a fixed point of this map is a new balance metric. So basically, it tells you what happens when you have a metric which is very close to be balanced. It tells you how far you are to the true balance metrics. So it's a measure of the balance metrics of, yeah. Okay, of the defect of being balanced when you're close in a neighborhood of a balance metric, if you wish. In particular, it will measures the convergence, the close to a balanced metric, it measures the convergence properties of this map. So what happens when you start with a Kähler metric, take the L2 product, pull back the fubini study metric. So let's say it's not the same metric. So I do it again. Take the L2 product, pull back, not the same metric. I do it again. And it is a fact of Donaldson's program that this iteration of L2FS, take the L2 product and pull back. If you iterate it, it would converge to the new balance, to the balance metric when it exists. And BP, in that case, will measure the speed of convergence of these iterations. So this is a very rough idea of what happens in our point of view on the proof of Donaldson. You want to control the differential of this map, right? So I want to point out here that this point of view of this map and looking at its differential, not in this language, but this point of view has been developed by Donaldson, but also following then Kähler, but also Fine, and then in the case of vector bundles, Kähler, Meyer, and Seyed Ali. But our point of view is to take seriously the fact that this is a real quantum object. And in particular, it is a Markov operator which characterizes the uncertainty introduced by quantization, right? So this is somehow our interpretation of this differential, which we're gonna use. So in particular, because it's a Markov operator, its spectrum belongs to 0, 1, right? Is discrete. And the first, the highest eigenvalue equals to 1 is associated to constant functions. And then the spectral gap of the Bayesian transform as a Markov operator is defined by the distance from this eigenvalue equals to 1 with the rest of the spectrum. And in particular, it will measure how fast iterations of this map, L2 and fubini study, converges, right? On the other hand, from the point of view of Berezin-Toeplitz quantization, it's a measure of the quantum noise introduced by quantization. So the fact is, it measures how a function blurs when you quantize things. In particular, it sends, if you wish, it will send a Dirac to a highly peaked Gaussian, which will have size 1 over p. So the Heisenberg uncertainty principle somehow, right? And our result in this setting is to compute an estimate of this spectral gap when p tends to infinity in terms of the first positive eigenvalue of the Riemannian Laplacian, so the Riemannian geometry of X, right? So highest order of quantization is controlled by the symplectic geometry. Next order, when p tends to infinity, so this tends to 0, is controlled by the Riemannian geometry of X, right? But in particular, this means that the spectral gap is strictly positive when p tends to infinity, because lambda 1 is strictly positive, right? Strictly positive, but tending to 0 as we approach the classical. Classical when there is no spectral gap because nothing blurs, basically. Things are exact in that point of view. And this should be seen, as I said already, as a global version of the Heisenberg uncertainty principle at the semi-classical limit when p tends to infinity, telling you that you cannot measure speed and position at the same time with infinite precision. Okay. In this context, it measures the speed of convergence of fubini study composed with L2, and which allows, with some work, to get a new method of proof of Donaldson's theorem and all related theorems, right? So quickly, when this was when nu does not depend on h, and unfortunately, all cases I've presented you before, so balanced and anticanonically balanced, use a measure that depends on h. And in that case, this operator, which is necessary, there should be iota star of S0 here. This operator is not the Berezin transform, something more complicated, but which you can deal with. And in particular, to establish the case of anticanonically balanced metrics, you need to deal with it. So it's some kind of intermediate case. But the hard case has been dealt with recently in a paper with Leonid Polterovich, which tells you that so the spectral gap, not of SP because it's it's not self-adjoint anymore, but take its self-adjointization. Well, I don't know if it's a word, but you see. And this has a spectral gap, which also can be computed in terms of the first positive eigenvalue of the so-called operator of variation of scalar curvature. So a more complicated operator of order 4. So remember, Laplace operator is of order 2. This operator is of order 4, which is completely reminiscent with the distinction between Kähler-Einstein of order 2 and constant scalar curvature of order 4. It's of course not at random. And also the estimate is that p squared instead of p. So it's much, much finer. So from the point of view, the spectral gap here tends much faster to p, but still there is an irreducible quantum noise which you can control and which allows you to provide a new proof of the first result of Donaldson, which is the hardest one because it deals with constant scalar curvature instead of Kähler-Einstein, which is easier, right? And also in the same paper, we dealt with the case of stable vector bundles endowed with Hermite-Einstein metrics, playing the role of a canonical matrix for vector bundles, giving a new proof of a result of Wang. So we have also a notion of balance metrics, and here is the first eigenvalue of the Kodaira Laplacian which appears, right? Okay, so I will briefly tell you a few words on the proof now, very briefly. So to prove such a result, we adapt a strategy of Lebon and Michel, which computed the spectral gap of semiclassical random walks on a Riemannian manifold. So we see Berezin transform on iteration of this Markov operator as a random walk on Riemannian manifold, and we want to adapt their strategy. In particular, we start with an estimate of Karabekov and Schlichten-Meyer, which is a standard estimate in Berezin-Toeplitz quantization, telling you that Berezin transform is almost the identity and functions up to the differential operator given by the Laplacian and an error, right? So if you forget about this, then if you add only this first term, this is exactly the statement of the theorem without error, right? The spectral gap is if you look at this operator instead of this operator instead of the Berezin transform, you directly have our result on the spectral gap. The problem is that the error is not L2. If you want to control eigenvalues, L2 eigenvalues, you need an error up to L2, and this is C4. It turns out that it's completely wrong, that it's L2. It's not true. It will be, it will be very contradictory. But you can deal with, using their strategy, you can show that the first eigenvalues first eigenvalues saying in a window close to 1, so the first eigenvalues starting from 1, so gamma 0, gamma 2, first eigenfunctions, their Sobolev norm is controlled by their L2 norm. So in particular, the C4 norm is controlled by the L2 norm. So for these eigenfunctions, you are able to estimate the eigenvalue, in particular the first few ones, in particular the first one. And this allows us to apply this to estimate eigenvalues. And so this is a brief slide explaining you so recently we also dealt with the next order case, where you have the next order formula. In that case, SP, actually it's self-adjointization, SP star square root is this operator. So this will have for effect to cancel this term, but also this term, you will be left with D. Applying the same method, you get the result. So there are analytic difficulties, but I'm summarizing. On the other hand, we also deal with the case of a vector bundle, where on the contrary, the analysis is not much harder than in the basic case, but there is some geometric subtleties. In particular, the naive notion of Berezin transform is not the correct one. So we did some new geometric input using the theory of Mamarinescu, interpreting quantization of vector bundles as quantization of symplectic vibrations. But yes, that will be it. So thank you very much.
Thank you very much. Est-ce qu'il y a des questions? Are there some questions from the audience? Je ne vois pas de main levée. Moi j'ai des questions. D'abord, est-ce que tu pourrais revenir sur la fin, la toute fin, là, parce que tu allais… voilà. Donc, qu'est-ce que tu appelles quantization of symplectic vibration?
Je devrais parler en français ou en anglais, là, du coup.
Oh, si tu peux le faire en français, c'est aussi.
Ici, oui, bon, en fait, bon, ça, effectivement, c'est un terme un peu fancy qui veut, en fait, quand on interprète un fibré vectoriel sur une variété comme, en fait, la quantification dans les fibres d'une fibration symplectique. Par exemple, si tu as un fibré vectoriel holomorphe sur une variété, tu peux prendre sa projectivisation, et si tu quantifies les fibres avec O1, mais seulement les fibres, tu prends les espaces quantiques dans les fibres, tu récupères E. Donc en fait, un fibré vectoriel, on appelle ça quantization in stages. Au lieu de quantifier toute la fibration, on quantifie d'abord les fibres, puis la base. Et en gros, c'est juste une interprétation, hein, de ce point de vue-là, mais c'est ça qui nous a permis d'arriver avec la correcte, la bonne définition de transformée de berezin, en particulier celle qui marche pour notre analyse. Je ne sais pas si j'étais clair.
Si, ça aide. Et est-ce que tu peux attraper les autres valeurs propres tout à l'heure, tu as attrapé la première valeur propre de l'opérateur de Leonid et du Laplacien,
Oui.
si j'ai bien suivi. Est-ce que tu peux attraper les autres valeurs propres avec ta méthode?
Oui. Toutes les valeurs propres, donc oui. Donc c'est ce qui est écrit. Enfin, ça se voit ici, n'est-ce pas? Tu prends toutes les premières valeurs propres up to quelque chose de fixé. Tu peux même aller un petit peu plus rapidement, d'ailleurs. Mais bon, notre résultat, c'est pour tout entier K, les K premières valeurs propres, les K premières valeurs propres sont approchées de la même manière. Ouais. Tu peux aller un peu plus rapidement que seulement fini, mais par contre, c'est pas vrai pour toutes les valeurs propres en même temps. Et le fait que ce soit pas vrai pour toutes les valeurs propres en même temps est complètement clair parce que lui, transformé de berezin a une image finie.
Oui, bien sûr.
Si tu réfléchis un peu à ce qui se passe, ça va pas marcher.
Et un autre détail, c'est qu'en fait, les théorèmes, quand tu as parlé là, de BBGZ et Takahashi, etc., l'input que tu as eu, que tu as fait, je ne sais pas si c'est clair pour les autres personnes, c'est que tu as amélioré la régularité, c'est ça? Tu as une convergence, tu as une convergence en norme CK, CK quel que soit K.
Donc c'est ce que je dis ici. Là, j'ai insisté. Oui, voilà. Convergence in the sense of current, ça veut dire in the sense of distributions. Donc, c'est très faible. Moi, c'est la convergence en CK pour tout cas, donc la convergence lisse. Et en particulier, pour un autre aspect du problème de Donaldson dont je n'ai pas parlé, qui est la vitesse de convergence des itérations de ce L2 et fubini study, c'est important, ce genre de choses. Donc, c'était ma motivation à la base, donc je suis content d'avoir… Ouais. Ici, c'est… attention, donc ici, c'est pour ça que j'ai rien dit ici. BBGZ, donc Berman, Buxom, Gage-Zeriahi, ils font au sens des distributions. Donc la méthode de Donaldson est plus forte pour ça. Mais Takahashi a réussi à juste appliquer la méthode de Donaldson ici. Donc c'est lisse pour lui.
C'est lisse déjà, ok.
Pour lui, c'est lisse ici. Et donc en fait, je donne juste une nouvelle preuve. Mais par contre, ici, il faut pas ici, c'est pas lisse. Donc, Takahashi, ici, il n'y a pas de… La méthode de Donaldson n'a pas été étendue dans le cas des solitons de Kähler-Ricci. En tout cas, à ma connaissance. Certains diront peut-être que c'est possible. Je suis sûr que c'est possible, hein, mais ça n'a pas encore été étendu. Et,
parce qu'il avait vu, il y a un point de vue application moment de l'équation Kähler-Ricci-Soliton. Il me semble
c'est ça. Qui?
Il me semble qu'il a écrit quelque chose en ce sens il y a quelques années. Bien après courbure scalaire constante. Non, je me trompe?
Mais qui?
Donaldson, il n'a pas une note ou un truc comme ça où il parle de l'équation de Kähler-Ricci-Soliton vue en tant qu'application moment?
Ah, il a une note pour, je pense, c'est plutôt pour Kähler-Einstein.
Ah, Kähler-Einstein, uniquement.
vu en... Bah, bon, bien sûr, le truc, c'est que si tu as une... bien sûr, Kähler ipsi soliton, c'est la version équivariante. Donc, si tu as l'application moment pour quelque chose, tu peux te dire, bon, bah voilà, il suffit d'avoir la version relative. Et dans ce cas-là, ça marche. Encore faut-il le faire. Mais oui, c'est pour Kähler-Einstein et c'est relié effectivement. Donc, typiquement, ici, Berman, Buxom, Getzereai et Takahashi développent là-dessus. Ils utilisent la quantification de la fonctionnelle de Ding. C'est ça. Parce que normalement, c'est la fonctionnelle de Mabuchi. Dans le cas de... ou une fonctionnelle de Ding, je ne sais pas trop. Et eux, ils font la quantification de ça. Donc, c'est ce qu'a fait Takahashi. En gros, c'est reprendre cette idée de Donaldson dans le cas, mais il l'a développé pour la quantification. Je ne pense pas que Donaldson ait fait quoi que ce soit du point de vue quantification, mais bon, que ce soit possible, voilà. Mais c'est plus dur. Donc, en fait, l'intérêt de ma méthode, c'est qu'en fait, ce cas-là est censé être plus facile. Donc, ma méthode est effectivement montre que la preuve dans ce cas-là est plus facile que le théorème de Donaldson, alors que la méthode de Takahashi est plus dure. C'est-à-dire qu'il faut, il y a des trucs à étudier. Il y a la fonctionnelle de Ding, il y a des trucs, enfin, du coup, il introduit, la géométrie est plus touffue. C'est pour ça que ça a pris si longtemps.
Ta méthode est
Alors
plus
que je simplifie.
versatile. Elle est plus versatile parce qu'elle marche dans différents contextes, en fait. C'est
C'est
ça ce que
ça,
tu dis.
c'est ça. Et, oui, oui, oui. Et
Est-ce que
je
tu penses que
pense.
tu pourrais la faire marcher dans le cadre de métriques Kähler-Einstein singulières
Ouf.
pour avoir des résultats de convergence, je ne sais pas moi, lisses, en dehors des lieux singuliers? Tu sais, par exemple, juste sur une variété de type général, avec fibré canonique, big NF. Donc, dans le cas, pas du tout Fano, mais dans l'autre cas, tu as
Oui, oui,
réfléchi
oui,
à ça?
bah, j'ai pas réfléchi à ça. Alors, je sais pas. Bon, je sais pas. C'est une bonne question. J'y ai pas réfléchi. J'ai réfléchi à d'autres cas lisses. Je préfère quand, quand c'est lisse. C'est une bonne question. Très bonne question. J'y ai pas vraiment réfléchi. Le problème, mais bien sûr, c'est est-ce qu'on a besoin, c'est le point clé, est-ce qu'on a besoin d'une estimée pour le noyau de Berman dans le voisinage des singularités? Si c'est le cas, ça va être compliqué. Si on peut se restreindre, si on a le droit si on arrive à se restreindre en dehors des singularités, alors ça pourrait marcher. Mais je ne sais pas si c'est. Donc, pour les singularités, dans le noyau de Berman, les estimées qu'ils font, elles sont là seulement, à ma connaissance, seulement dans le cas des surfaces de Riemann. C'est Marinescu,
Oui,
Hugo, vrai.
ouais, ouais.
Et dans ce cas-là, oui, je suis sûr qu'on pourrait faire quelque chose. Ce serait pas si intéressant parce que bon, surface de Riemann, mais je suis sûr qu'on pourrait faire quelque chose dans ce cas-là, au moins comme time model. Sinon, je sais pas. Il se peut qu'on peut contourner le problème. C'est une très bonne question, je pense. Oui, très bonne question. Si ça marchait, je serais très. S'il y avait une approche, je serais très. Si tu avais une idée d'approche, je serais très intéressé, effectivement.
Il y a autre chose. Il y a les métriques aussi regardées par Abdellah Dili, tu sais, les métriques à courbe scalaire constante à poids.
Ah oui, 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 ça, je suis sûr que ça passe.
Ça,
Du coup, tous les trucs à poids que j'ai regardés, c'est bon. Si tu
ça
veux. Il y
fonctionne.
a aussi. Oui, oui, oui. Alors, je sais, bien sûr, il faut regarder, mais en fait, c'est. Oui, oui, oui. Donc, ça, c'est ce que j'essaye de vendre aussi. C'est que si tu rajoutes tout, oui, ma méthode se déforme très, très lisse, enfin, de manière très lisse, si tu rajoutes des poids. Donc, je pense que ça, c'est un vrai atout. C'est vraiment la méthode marche telle quelle. Il faut juste voir que la quantification de Bayes-Toeplitz suit, enfin, si tu rajoutes des poids, ça se déforme de manière lisse en les poids, ce qui en fait, grâce à la robustesse de ces méthodes, est toujours vrai, tant que tu vas pas trop loin. Il faut rester dans des déformations, petites déformations. Tu peux pas, les dégénérescences, on est perdu, mais tant que tu es dans un espace compact de déformation, c'est bon. Et donc oui, il y a d'autres types de métriques dans le cas Kähler-Einstein. Eux, ils regardent des trucs qu'ils appellent theta balanced. Il y a aussi alpha courbure scalaire, c'est ça? Il y a aussi des
Alpha.
notions de courbure scalaire à alpha près. Il me semble que d'ailleurs, tu as un papier là-dessus.
Oui, oui, non, mais ça, oui, mais après, ça a été nettement amélioré. Je dis le truc, le résultat optimal récemment, c'est celui je pense, d'Abdellah, où il a, tu peux regarder sa thèse, où il a une notion de métrique à courbure scalaire à poids
qui recouvre notamment l'équation extrémale et d'autres mêmes types d'équations.
C'est un étudiant de
non,
ouais,
d'Apostolov.
D'Apostolov, oui. Oui,
la Dili.
Ouais. Ok, je vais regarder, mais oui. Après, ouais. Après, il faut aussi, j'ai pas parlé, il y a le cas métrique extrémal, qui est un peu l'envers, constante scalar curvature du cas Kähler Soliton. Et ça aussi, ça marche, ça serait plus compliqué. Oui. Ouais. Grâce à notre
tu as écrit un résultat dans ce sens, dans le cas extrémal
Non, bah déjà parce que, enfin bon, du coup, j'ai un peu, je sais que ça marche et ça, il existe déjà. C'est Sano et Tipler et Seyedali, mais aussi Hashimoto et aussi Mabuchi. Ils ont tous des versions.
Les notions sont un peu différentes, tu vois. Les notions sont un peu différentes et elles utilisent toujours la notion d'application moment.
Oui. Donc la bonne notion, celle que j'utilise, donc la bonne, de mon point de vue, celle que j'utilise, c'est celle de Sano et Tipler.
Ah, d'accord.
Qui, je pense, est équivalente à une autre. Que celle de Seyedali. Ouais, mais je suis pas. Ouais.
Non, c'est pas clair qu'elles soient toutes. Je crois pas qu'elles soient claires. Si, peut-être un article de Tipler qui montre qu'elles sont équivalentes pour 2 d'entre elles sur les 3.
Ouais, mais j'utilise celle qui va bien, c'est celle-là, hein, c'est écrit là. C'est exactement celle-là.
Ah d'accord, c'est exactement celle-là.
Oui, et c'est aussi celle qu'utilise Berman, Wittnystrom et Takahashi. Hein. Donc, bon. Bon, moi, c'est celle qui marche. C'est clairement celle-là pour moi, du point de vue de ma méthode. Après, je sais pas. Ouais.
Bon,
et dans ce cas-là, métrique extrémale avec cette version, oui, ma méthode marche. Et si on rajoute des poids, bah, il faut voir au cas par cas, bien sûr, mais oui, je crois. Je crois que oui.
Est-ce qu'il y a are there any extra questions or comments? We have a large audience today, but people are shy. Okay, so I think it's time to thank warmly Louis for his excellent talk. So I invite you to do at least
well, thank you very much for inviting me.